I want to explain this one by drawing some diagrams that might be a little easier to understand than those and better than those. On the test, you're not going to have a graph. You're going to have a series of drawings. And I'm going to turn this scenario here into a series of drawings, diagrams with individual forces and net forces. So in this particular scenario, there was a, looked like this before I did all this to it. A balloon, a latex balloon, was inflated and dropped from a roof. So here it is at the moment it's released. And it's falling, falling, falling. At some point it reaches terminal velocity before it gets to the ground. And then it continues falling to the ground. And then it touches the ground, sort of bounces, releases from the ground, and goes back up. And eventually gets to its high point. So it's dropped from way up here, bounces down. When it goes up, it doesn't go up as high as the point from where it was released. And the graph is net force, which you could also think of as acceleration. But it's helpful to think about individual forces. So I'm going to draw them. So I'll just call this will be number 1 right here. I'll number all my drawings. So in picture number 1, this is the balloon right after it's been released. And the thing that's going to be constant through all these is the weight. So the weight, I'm going to try to keep that arrow the same length. Right as it's released, it doesn't have any velocity, so there's no drag yet. So the net force is equal to the weight, basically. I'll just write net force down, and it's the same as the weight. Now as this starts to fall, there's going to be some drag. And the way I've got it right now, the drag is still not as strong as the weight, so there's still a downward net force, but it's weaker. And then as it keeps falling, it's going to fall faster until the drag is equal to the net force, or sorry, is equal to the weight. And then the net force is 0. So let me try to match that up to what's going on in this picture. I decided on my other answer I'm going to have a little dotted line just for reference. This would be the force of gravity. This is the weight of the balloon, and it's a downward force, so it's negative. And this is so the balloon's going to start like that, and I don't know exactly how this is going to happen. I would guess this is going to be kind of a curve like this. So this is where my picture number 1 takes place. Somewhere along here, this is where my picture number 2 takes place. And my picture number 3 can be for anywhere in between there. Hold it so I can see it. So I've got a strong downward force. That's why this is negative, and as far down as we're going to get. And then we're still in the negative region. But then when we get to here, these two individual forces cancel out, and we have no acceleration and no net force. Now here's where it touches the pavement, and here's where it's fully compressed, and here's where it loses contact with the pavement. This is going to get a little hairy, especially the losing contact point. So when it first starts to touch the pavement, I would say if you're the ball, life is not a whole lot different than it was right before you touch the pavement. After you start getting squished here, then things are going to change for you. But right there, the center of mass of the ball is probably still going down. So at the moment it touches, it's really hard to distinguish between the moment of touching, the moment right before the moment of touching and the moment right after the moment of touching. But our pictures will look quite different. So I'm just going to say at the moment that it touches, the ground hasn't really started to push very hard on it yet. As it squishes and squishes and squishes itself into the ground, then the ground's going to push harder. But for this next picture, two things. The ball is still moving downward, or at least its center is, because it hasn't fully compressed and gotten to its lowest point. So there's still going to be some drag on it. And it's still going to have weight. But it's also going to have the force of the ground, which I'll call the normal force, acting on it. So at this point, well, if you look at the three forces that I've drawn, these two cancel out, and that's positive. So this is going to be positive net force, just equal to that normal force. Now in this picture, it stopped moving. It's at its lowest point. It's totally squished in. And it would be like a spring here. By the way, this would be a little more complicated than what you would need to do on a test. What I'm drawing is implying that you need knowledge of how balls compress when they hit the ground. And you don't for the test. But still, this is good practice. So if you have a spring that's uncompressed and a spring that is compressed, this is pushing harder against the earth than this is, and therefore the earth is pushing equally hard against that and equally hard against this. So what I'm getting at is when it first touches, the normal force of the earth pushing up isn't very hard, but when it's totally squished down here like this, it's flattened itself out, now the normal force of the earth is really big. I'd make it maybe even bigger if I had room here. The weight's still going to be the same, and there's no drag anymore because it stopped moving. So the force is going to be big and upward. And exactly how this force increases over time, I'm not really sure, but I'm going to show it kind of going like this. I don't know if it would go like that or straight, but let's just show it increasing. And I'm thinking that the force of the compression, force of the squeezing on the ground, is probably greater than the force of gravity in the beginning. Hope you've been able to see this. I'm sorry if you haven't. So this should actually be really tall here, I think. And then this is going to reverse itself as the spring, which is, you can think of the ball as a spring, as the spring decompresses, it's not going to push as hard against the ground, so the ground's not going to push as hard against it. So the upward force on it is going to decrease again. So this is compression, the ground exerting maximum force on the ball when it's fully compressed, and then exerting less. I'm just going to go over here to number 6. So number 6 is back like this again. And this is kind of strange. So I'm going to show just as much force as of the ground pushing on the ball as I did when it was just touching. When it's just releasing, the ground is still pushing up, just like it was before. And we still have the weight of the ball. That's never going to go away. And drag now is going to be just like it was here, except here the ball is going down. Now the ball is going up, so drag is going to be like that. So I've still got a negative force here, at least. Yeah, so these are outweighing that, and it looks like it's still negative. but I've got this going to 0. So in my diagram before, you can see what I did. I kind of, instead of getting to 0 right there, I went negative before I got there. Let me do the next picture. This will be number 7. This will be right after the ball has let go of the ground, just a moment after it's gone from the ground. Now we have drag, which is just about as strong as it was a moment before, and we've got weight, which is as strong as it ever was, but we have no normal force. The ground's not pushing up anymore. So this, compared to the beginning, at least the way I've drawn it, it looks like we have twice the downward net force that we had in the very beginning. So that's why instead of having net force here at that dotted line, I've made it even lower. So sometime right after the ball loses contact, right after the ball loses contact with the ground, if this is where this is the boundary between touching and not touching, right after it lets go, it's going as fast as it can go, it's going upward just about as fast as it had been going downward. Actually, you know what? This should be a little bit less than that, because when this ball hits the ground, squishes, and then bounces back, it's going to lose some energy. It's not 100% efficient, so it's going to go up a little bit slower than it went down. So I'm going to make this drag a little bit lower. Anyway, we're still going to have, after it's released, we're going to have two forces that are downward and no upward forces. So that goes to down here. Now, as the ball bounces higher and higher, it's higher off the ground, it's been going back up for a while, it's going to go slower and slower. And that's not going to change this weight, but that is going to change the drag. So as it gets higher, the weight's the same, but now the drag is smaller. And eventually, it's supposed to be 9. When it gets to its highest point, the drag is going to stop, and we'll just have weight again. So I've left out my net force on these diagrams. This would be net force is really strong and down. Oh, no, it's kind of downward. Here the net force is really strong and down. Here the net force is not quite as strong and down. And here the net force, I'm just going to say weight equals net force, is down, and it's the same as weight. So what's going to happen is something like that. So let me just go back through this, talking about this graph. In the beginning, the net force is negative, and this is the ball in free fall, or the balloon in free fall. As the balloon falls, it's going to go faster and faster and faster until it gets to its terminal velocity. Now, this is a negative net force, so it's going to be faster downward. And when it gets to here, it's not going to be accelerated anymore downward. It's just going to fall at the same speed. And right here is where the ground pushes it up, and as it squeezes itself into a ground and comes to the stop, the ground pushes harder and harder because its compression pushes harder and harder. And then it starts to bounce back up, and as it decompresses, it doesn't push as hard against the ground, so the ground doesn't push as hard against it. And somewhere around here, it releases itself entirely from the ground. It's going just about as fast here as it was going right there. And right there, the force of drag was equal to its weight. So here the force of drag should be just about equal to its weight, but it should be the opposite direction. So we should have a force that's about 2 times the weight, but negative. Maybe not quite that, because it doesn't quite bounce up as fast as it bounces down. So here it's got drag pushing it down plus weight pushing it down, and when we get to here, it's at its high point, just has weight pushing it down. And if we followed this, everything would just repeat. It would go like it would be this would go back to here, and the ball would fall and do all this, except with every cycle, I keep calling it a ball, it's a balloon. With every cycle, these forces would get, the impact force would get smaller, and this speed and therefore the drag on its way up would get weaker.